back, World War II.
Right.
Think about the bombing of Dresden, 1945, unguided bombs, just widespread destruction. An estimated 25,000 civilians killed. Just devastating.
That's a horrible example, yeah. Total war.
Now, fast forward to conflicts happening right now.
Yep.
We have incredibly advanced weapons, right? But often, the result is fewer casualties overall, much less of that citywide destruction.
It seems paradoxical almost.
Exactly. It's this huge shift.
Yeah.
So the big question for our deep dive today is, what's actually behind this? How did war change so fundamentally?
Well, the answer, and it might seem a bit strange at first, it lies in something incredibly small. It's what we're calling the silicon shield.
Silicon shield, okay.
Yeah. So today we're going to dig into how these tiny chips, semiconductors, haven't just, made weapons smarter. They've completely changed warfare itself.
From blunt force to
incredibly precise strategic strikes. And maybe surprisingly, this has actually changed the nature of conflict, potentially even reducing civilian harm in many cases.
Interesting. And where are we getting this from?
We've done a pretty deep analysis of various materials, and importantly, we've got some unique industry perspectives too, specifically from Orbit and Skyline. They're right at the forefront of semiconductor solutions for these kinds of applications.
Okay, great. So our mission for you listening is to unpack this surprising role semiconductors play. We'll look at the specific tech involved and, crucially, why having your own semiconductor manufacturing is now so vital for national defense.
That's the plan.
So let's maybe start with a bit of that historical context. War has always been with us, sadly. World War II, as I mentioned, the deadliest ever. 70, 80 million lives lost.
Just staggering numbers.
And the approach back then, it was often about maximum destruction, right? Tanks, grenades, carpet bombing, designed for brute force. Collateral damage was, well, almost expected.
Part of the strategy, unfortunately.
But today, modern nations really prioritize precision. It's a totally different mindset compared to even just a few decades ago, let alone the 1940s.
It really is. It's a massive shift in thinking and doctrine. Modern battles are increasingly fought remotely. The idea is to keep your own forces safer, further from harm's way, and ideally reduce that collateral damage.
Remotely, like drones.
Drones are part of it, yes, but think about air combat too. It's now mainly fought in what's called the Beyond Visual Range domain, BVR.
Beyond visual range.
Right. The days of close-in dogfights, like you see in old movies where pilots could literally see each other, mostly gone.
Really?
Yeah. Today's fighter jets carry missiles that can hit targets maybe 200 kilometers away, way beyond eyesight.
Hold on, 200 kilometers. So the pilot isn't seeing the enemy plane at all. How does that even work reliably?
That's exactly the point. It works because of extremely sophisticated electronic systems, advanced sensors, powerful radars, and all of it fundamentally relies on complex semiconductor technology.
Chips again.
The chips again? They're the tiny brains processing all that sensor data, allowing a pilot or even an automated system to see and engage a target that's far over the horizon. It's translating radar pulses, sensor feeds into a clear picture.
And you're saying this move to BVR, this reliance on electronics, actually leads to less harm?
The evidence suggests that yes. Precision targeting means you're hitting the intended military target, not the surrounding area. So compared to those older, blunt methods, you see a demonstrable reduction in civilian harm and infrastructure damage. It's a key outcome.
And it's these integrated circuits, ICs, that are making this possible. We know them from our phones, our computers, satellites, making everything faster, smarter.
Exactly.
But it's kind of mind-blowing that the same basic tech is also making weapons smarter, faster, and just incredibly accurate.
It is. These ICs are the absolute core of modern guided missiles, advanced radar systems, unmanned drones, surveillance platforms, everything.
What are they actually doing inside these systems?
Well, think about processing power. They're handling just massive amounts of data incredibly quickly. This allows for things like precise targeting calculations in real time.
Okay.
They enable missiles to follow complex, adaptive routes to avoid defenses, and they ensure secure, encrypted communication links, which are vital. It's this capability that shifts warfare away from just overwhelming force
To these focused strategic strikes, minimizing the unintended damage.
Exactly that. Focused strategic strikes.
Okay, I think everyone listening gets the what's, but the how is still kind of amazing. How do these tiny, tiny pieces of silicon achieve that level of precision? I mean, it sounds almost like science fiction.
It does feel that way sometimes, but let's break it down a bit. Think of it less as one magic chip and more like a whole team of highly specialized electronic components working together inside the weapon system. We can maybe group them by function.
Yeah, that sounds good. Like, what are the key jobs?
Okay, first up, let's talk about the system's eyes and ears. That's electronic warfare, EW, and radar.
Seeing the enemy, basically, and
Yeah.
maybe messing with their systems.
Pretty much. EW and radar systems are built on a whole range of semiconductor technologies, things like CMOS, gallium nitride or GaN, gallium arsenide, silicon germanium, different materials for different jobs.
Okay. Why so many?
Well, for example, GaN chips are really good at handling high power for radio frequencies. So they're used to amplify signals in powerful long-range radars or even in electronic jammers. They give the system its loud voice.
Got it. Power.
Then you need to hear the faint whispers, too. For receiving weak signals, you might use other specialized chips, like low-noise amplifiers, maybe built using silicon germanium or something called FEMT processes. They make sure the important signals aren't lost in the noise.
So loud voice, sensitive ears. What else for radar?
Then there's steering the beam. Modern AESA radars, that's active electronically scanned array, they don't physically move the antenna much. They steer the radar beam electronically using tiny RF switches and phase shifters. It's incredibly fast and agile.
Wow. Okay, so the radar dish doesn't spin like in the old movies.
Not usually on these advanced systems, no. It's all electronic steering. And then, of course, you need high-speed converters to translate analog radio waves into digital data and back, plus specialized processors like FPGAs and DSPs to make sense of it all, incredibly fast, and radiation-hardened components for reliability in harsh environments.
Okay, that's a lot just for the eyes and ears. So once it sees the target, how does it actually get there? The guidance part.
Right. Next key function, guidance and navigation. This is all about making sure the missile or drone hits exactly what it's aimed at, even if things get tricky. Reliability here is paramount.
Tricky like GPS gets jammed.
Exactly like that. GPS is great, but it can be denied or spoofed, so systems need a backup. That's where inertial navigation systems, or INS, come in.
Inertial, meaning it senses its own movement.
Precisely. They use tiny semiconductor-based sensors called MEMS microelectromechanical systems. Specifically, accelerometers to measure acceleration and gyroscopes to measure rotation.
Like in my smartphone that knows when I turn it.
A very similar principle, yes, but vastly more precise and ruggedized. These MEMS sensors constantly track the weapon's motion, calculating its position and path without any external signals. They're often packaged together into a compact inertial measurement unit, or IMU.
So it can navigate blind, essentially.
It can, and when GPS is available, dedicated GNSS receiver chips provide that absolute position. Modern ones have sophisticated anti-jamming and anti-spoofing capabilities built right in.
And chips process all this.
Yep. Digital signal processors, DSPs, and microcontrollers, MCUs, are constantly crunching the data from the IMU and the GNSS receiver, running complex algorithms to make tiny adjustments to the flight path, keeping it precisely on target.
Incredible. It's like a tiny, self-contained, self-correcting brain.
Yeah.
What about gathering intelligence, surveillance?
Good lead into the third area, surveillance and reconnaissance. Collecting information is key. Here you see image sensors, similar tech to digital cameras, CMOS or CCD for visible light and night vision, but also specialized infrared detectors for thermal imaging, seeing heat signatures. These use different materials like indium gallium arsenide or mercury cadmium telluride, bonded to readout ICs or ROICs to process the thermal data.
So they can see in total darkness or through smoke.
Exactly. And then there's radar again, but used differently. Synthetic aperture radar, SAR, can create detailed ground maps day or night through clouds. This needs those high-power GaN amplifier chips we mentioned, the sensitive low-noise amplifiers, and again, super-fast converters to handle the complex radar signals.
And processing all that imagery and data must be intense.
Hugely intense. That's where you see high-performance FPGAs, systems on a chip, SoCs, and increasingly dedicated AI chips. These often use the most advanced manufacturing processes like FinFET technology.
AI on the drone itself.
Yes, AI at the edge. It allows the platform, the drone, the satellite to analyze data on the spot, identify targets or threats, and make decisions much faster than sending everything back to a ground station. Real-time intelligence. And underpinning all this, you need memory chips like DRAM and SRAM, secure microcontrollers to protect the system, and robust RF transceivers for sending that processed intelligence back securely and quickly.
Okay, that deep dive really paints a picture. It's this incredibly complex ecosystem of specialized chips for sensing, thinking, guiding, communicating, all working together.
It really is.
So, stepping back from the tech specifics,
Hmm.
what does all this mean for the bigger picture, for national security, for global power dynamics? It feels like more than just better weapons.
It absolutely is more than just better weapons, and that brings us squarely to this concept of the silicon shield.
The shield made of chips.
Exactly. Think about it. Many countries, maybe most developed countries, can go out and buy advanced defense systems, missiles, jets, drones.
Right, the arms market is huge.
But only a very, very small handful of nations have the actual capability to design and manufacture the cutting-edge semiconductor ICs that are the heart, the brain, the senses of the systems.
So owning the system isn't the same as owning the key technology inside it.
Precisely. And these aren't just off-the-shelf commercial chips you put in a phone. They're often classified commercial, military, space grade. Military systems especially have to work in extreme conditions. Think temperatures from maybe -40 Celsius up to 150 Celsius, intense vibration, radiation.
They need to be incredibly robust, fail-proof.
Absolutely fail-proof. Lives depend on it. And because these chips are so critical and the technology is so advanced, access to the really high-end military-grade ICs is tightly controlled. Export regulations, national security restrictions.
You can't just order them online.
Definitely not.
Yeah.
And this is the crux of the silicon shield idea. If you don't have a secure, reliable, domestic capability to design and manufacture these critical semiconductors, you could be cut off from the supply chain right when you need it most, during a crisis, a conflict.
Your advanced weapons become useless without the chips.
Or you can't build new ones or repair existing ones. There's a great analogy used in the materials we looked at. These ICs function as the sensory organs, the eyes, the ears, the brains of missiles, drones, UAVs. They are absolutely essential for the mission. Lose access to them, and your advanced military is effectively blind and deaf.
That's a powerful way to put it. So this capability, this silicon field, isn't just about technology. It's profound strategic leverage.
Immense strategic leverage.
And tying it back to what we discussed earlier, having these precision strike capabilities enabled by these chips, it doesn't just help win battles. You're suggesting it can actually deter adversaries, make them think twice before starting a conflict.
That's a key aspect, yes.
Yeah.
The ability to strike precisely with limited collateral damage changes the risk calculation for potential aggressors. And we have seen this play out, arguably, in recent global conflicts. It allows for responses that are proportionate, targeted, without necessarily escalating to full-scale war.
Which, compared to the devastation of past world wars, is a fundamental shift. It seems this pursuit of precision, driven by silicon, has paradoxically made conflict, when it does occur, potentially less catastrophically destructive overall.
That's certainly one interpretation, and a significant one, and it's important to acknowledge the human expertise behind this. People like Vipul Sharma, mentioned in our sources, a principal VLSI design engineer with over 2 decades of experience,
Right.
and companies like Orbit and Skyline, with their deep engineering bench strength built over 15 years, they are the ones actually designing and enabling these incredibly complex chips. They're literally building the brains we've been talking about.
So wrapping this up,
Uh-huh.
we've seen how these tiny silicon chips have utterly reshaped warfare. They've made it more precise, yes, but they've also revealed this new dimension of national security. The security that comes from being able to actually make these vital components yourself.
The silicon shield.
The silicon shield. And this leaves us and you listening with a really important question to think about. In a world that's increasingly interconnected, increasingly reliant on technology, how might this silicon shield affect global stability in the future? How does it shift the balance of power, not just on the battlefield, but maybe even in diplomacy, in trade negotiations?
It really does invite you to think deeply about that constant interplay between technological leaps and geopolitical strategy. How something as small as designing a circuit pattern on silicon happening in specialized factories could genuinely be shaping the future of global security and peace. It's something to keep watching.